Okay, so today we will talk about conservation principles. So what is the context in which these principles arise? It's when we study systems that evolve with time. Okay, so that's the context. So let me say a little bit more about all this pretty much by examples. So we'll consider a few examples from which it will be clear what a conservation principle means and what sorts of systems we will consider and so on. So here's an example. So what's my system? So here's the description of the system. Imagine we have all the integers marked off on the number line. So it's 0, 1, 2, 3 and so on, minus 1, minus 2, minus 3. Okay, so I have the number line on which all the integer points are marked. And what I do, so what's my system? My system consists of, let's call it 4 coins placed at 4 positions. Okay, on this set of integers. So for a start, here's what I do. I have 4 coins, say one of them placed at minus 1, another placed at 0, 1 and 2. So here are my initial positions. I place 4 coins on these 4 integers. Okay, so this is my initial configuration of the system. So this is what you would call your initial configuration. So this is what happens at, let's say, time t equal to 0, and my system should now evolve with time. Okay, so then what you have is a rule which tells you what happens at every instant of time. Okay, so let's imagine that here time is not quite a continuous variable but rather a discrete variable, which means say at time t equal to 0 the system looks like this, at time t equal to 1 it will change to something else, at time t equal to 2 it will change again and so on. Okay, so the system changes at time steps t equal to 0, 1, 2, 3 etc. So what's the rule for evolution of the system? So let's call this a move. So what are the allowed moves? How do we, let's call this allowed moves or rules for changing the system. So at time t equal to 1, here's what you're allowed to do. You pick any 2 of these 4 coins. Okay, so here's the allowed move. Pick any 2 of the 4 coins. Okay, so choose any 2 and do the following: move one of them k steps to the right and the other k steps to the left. Okay, so move one coin k, where k can be any number, k steps to the right, and move the other coin k steps to the left. Okay, so here's a rule for evolving the system. So let's sort of look at one possible trajectory that the system might have taken. So let me only note the 4 positions of the 4 coins. So at time t equal to 0, so let me just say here is the value of time. So at time t equal to 0 I have the coins, so here are the positions of the coins, they're at minus 1, 0, 1 and 2. Now at time t equal to 1, what am I supposed to do? I am supposed to pick 2 of these 4. So let's say I picked minus 1 and 0, suppose I picked those 2, and what I am supposed to do is move one of them k steps to the right, the other k steps to the left. Okay, so imagine I moved say 0 3 steps to the right and minus 1 moved 3 steps to the left. Okay, so that's the move that I carry out. So minus 1 moves to minus 4, 0 moves to 3, and these 2 stay as they are. Okay, this could be one thing that happened in the next time step. Then at time t equal to 2 I repeat a move, meaning I again pick any 2 of these 4, move one of them k steps to the left, the other k steps to the right. Okay, and here k can be anything. So here k, I mean, it just makes sense to be let's say at least 1. So if you don't move them, nothing much happens. So let's say it's at least 1, it's an integer at least 1. Similarly, so I could have, so here I can have repetition. So for instance, I can choose 1 and 2 in my next step and move 2 1 step to the right and 1 step to the left. So here's what I could have gotten at the next step if I had chosen these 2. So in the first step I chose these 2. Here I move one step to the left, 2 one step to the right. So there are 2 coins now placed at the position 3 for instance, and so on. So you can now imagine how this game plays out. The system evolves at each time step, and at say at time n, whatever be the configuration at time t equal to n, at time t equal to n plus 1 you should take 2 coins out of that configuration and move them in the described fashion. Okay, so the system evolves with time in this fashion, and as you can imagine there are many possible trajectories, there are many different things that can happen depending on what you chose and how much you moved it and so on. So here is the question. There are 2 questions. Is it possible for the system at some time t, so can all the coins coincide at the same location? At some time t, meaning as the system evolves, is it at all possible for all the coins, so they are moving in some funny fashion, is it possible for all of them to somehow coincide at the same point? Okay, so that is question number 1, and here is another question. Can all the coins move to the negative part of the real axis? Move to the move to non-negative integer positions. Let's write it like that. Move to non-positive So what do I mean by the non-positive integer positions? That's numbers 0, 1, 0, minus 1, minus 2, minus 3 and so on. So is it possible for all the integers to somehow, for all the coins to somehow move in such a way that they lie on the negative part of the real axis? Okay, so there are these 2 questions, and what we want to understand is, somehow by analyzing the moves that are allowed for the system, can it somehow happen that at some time t that configuration A happens or configuration B happens? Okay, so those are the questions that we want to answer. And here is the answer, which is based on the following important observation. Notice that if the rule, so let's define a function. So let me say the configuration. So suppose I am given a configuration. So what is the configuration? It is just the 4 positions of the first coin, the second coin, the third coin and the fourth coin. So I have these 4 positions. Now let us define a function. So let me call this configuration as C. Let us define a quantity, let us call it gamma of C. Okay, it is a quantity which depends on this configuration C. Let us define it just to be the sum of these 4 numbers, n1 plus n2 plus n3 plus n4. Okay, so to each configuration we associate this number, which is the sum of the 4 positions. Now observe what happens as the configuration evolves. Okay, so let us come back here and write down these numbers. So here are my configurations, if you wish. So let me now call it configurations. And let us compute the gamma function, okay, on each of these configurations. So now observe that the very first guy has let us see 2 plus 1 3 minus 1 is 2. Now the second fellow here is 3 plus 3 6 minus 4, which is 2 again. This is 6 minus 4, which is 2 again, and so on. So here is what you will observe, pretty much any configuration that you can obtain by applying the rules will always give you the same value of gamma. Gamma will always be a 2. Okay, and this of course not at all surprising if you really analyze the rule properly. So what does the rule say? Well, you pick any 2 of these 4 numbers, n1, n2, n3 and n4, you pick 2 of them, you increase one of them by k and you decrease the other by k. That is what the rule says, and of course doing that will not change the sum of the 4 numbers, right. So one of them will increase by k, the other goes down by k, and the total sum remains a constant. Okay, so as the system evolves, the function gamma does not change. That is the key observation here. So observe that as the system evolves, the gamma function remains the same. Okay. So this is often expressed by saying that gamma is conserved. Okay. So of course, you know what finding a quantity which is conserved may not be very easy in any given situation, but if the evolution, the rules for evolution admit a conserved quantity, it often makes answering questions like what we posed somewhat easier, at least in some cases. So let us now use this to answer our first question. So the first question said, can it happen somehow that all the 4 coins are located at the same point? So I want to know, let us call this integer as p. Can it happen that my configuration, so can I land up with a configuration that looks like p, 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 p? That is the question, okay, as time evolves. Now let us see if this is possible. So what is gamma? The gamma function for this configuration is just the sum of the 4 numbers, that is 4p, and what do we know? The gamma function does not change, right. So the starting configuration had gamma function as 2, so of course whatever configuration you can get at some time t had better also have the same gamma function. So if at all it is possible to get to p, 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 then this equation must be true. 4p must be equal to 2, or in other words p is half, okay. But observe that is not possible because p was supposed to be an integer, right. P is the position of the coins, so p is an integer, so this is not possible. So it is actually not possible to get all 4 coins to coincide at the same point, okay. Now I leave the second question as an exercise. Try using the same argument, just the same, apply the same gamma function to conclude that it is not possible for all 4 coins to somehow move to the negative part of the real axis, okay. So the second question is an exercise for you to try. Now let us do some more examples. So here is example 2. So here is again, you know, we need to describe a system. So now my system is the following, it's a configuration of 4 points on the plane, okay. So what are my 4 points? So let us just say I have one of them is, so they are the 4 corners of the unit square. So these are my, this is my initial configuration, okay. So what are these points? Maybe I should have colored them yellow. So here's 1, here's 1. So these are 0, 0, 1, 0, 1, 1 and 0, 1. So I place 4 coins on the plane, and now what do? I need to tell you how the evolution takes place. So what are the rules for evolving the system? So here are the allowed moves. At each time t we apply, you are allowed to do the following, you are allowed to apply one of the following 3 linear transformations. Okay, what are the 3? I will call them f1, f2, f3. So there are 3 functions which are all linear transformations. What you can do is you can apply that function to all 4 points at once. So let us first write out what are these linear transformations. So f1 is defined as follows, f1 of xy is 2x comma half y. That is one function. Second function f2 xy is y comma x, and f3 of xy is given by, see, it is 2x plus 3y, 3x plus 4y. Okay, so here is what we do, we explicitly give 3 linear transformations, 3 transformations of the plane, and a move consists of the following. At each time t, you pick one of these 3 possible linear transformations and you apply it to the 4 points. Okay, so let's give an example. So here's the configuration. So again, here's time. So what are the configurations? Well, at time t equal to 0, the initial configuration consists of the 4 points 0, 0, 1 0 1 1 sorry 0 1 and 1 0. So that's where my 4 coins are placed. Now what happens at time t equal to 1? So maybe we will should probably have written like this. That's the position. At time t equal to 1, I pick one of these 3 linear transformations. So let's imagine I pick the transformation f3. Now what I'll do is I'll apply f3 to all these 4 points. Okay. So after all it's a transformation. So what does f3 do to 0 0? Well, we have to calculate, but it's clear it maps it to 0 0 again. If you take 1 comma 0, it maps it to 2 comma 3. If you take 0 1, it maps it to 3 comma 4. And if you take 1 1, it maps it to 5 comma 7. Okay. So these 4 become the new positions of the 4 coins. Okay. So observe those are actually the 4 corners of parallelogram. So we have sort of looked at these things when we looked at the transformations. So this is so I don't know, it's 2 comma 3, 3 comma 4. So it's some parallelogram like this. So those the corners of this parallelogram are now the new positions of the coin. So originally they were the corners of a unit square. After at time t equal to 1, maybe it became a parallelogram. Okay, and time t equal to 2, you again pick one of these. You pick f1 or f2 or f3. You apply it to this parallelogram. It will transform to something else. Okay, and those become the new positions, and so on and so forth. So the evolution is given by the following rule. You pick any one of the 3, f1, f2 or f3, and you apply it to all 4 points, all 4 corners. So now here's the question. The system now of course evolves with time, and we ask a similar thing at some point of time. Is it possible for the system to be in the following configuration? So question, can the system reach the following configuration? So well, what configuration do we want? We want the 4 points to be the corners of a rectangle of side 3 and 2. So is it possible as the system evolves for it to somehow get these 4 points to lie on the corners of a rectangle of sides 3 and 2? Okay. So that's now the question. So again, here's the answer, which again follows the same prototype as we did for the earlier case. What we will try and do is to find a conserved quantity, try and find a function which does not change with time. Okay. So as the configuration changes, the function however remains the same. Okay. And what's the function here? Well, it's rather easy, the gamma function. So let's define gamma of a configuration. So let C be some configuration of the 4 points, and we define the gamma function as follows. Gamma of a configuration is just the area of the parallelogram. So in general it will always be a parallelogram. So it's the area of the parallelogram with vertices being the 4 points of C, with vertices being the points in the configuration C. So remember now C now denotes, it's a set of 4 points P1, P2, P3, P4. Okay. So now the function here is just the area function. Okay. And again observe that, so this is something that we did last time. The area is just given by, so if I apply, so now observe that last time we had the following fact, that if I have a region R, so let's recall the following. If I have a region R on the plane, let's say a square or pretty much any polygon, and I apply a linear transformation to it. So I apply a linear transformation, and this might become some parallelogram here. This is the image f of R. Then here's what we said, the area of f of R divided by the area of R. So this was what we call the area dilation factor, can be simply computed by just taking the determinant of the matrix representation of f. So this we said is just the absolute value of the determinant of the matrix encoding of f. Okay. So this is the area dilation that the transformation f induces. So let us do it in each of these cases. So I have my function f1 is just given by 2x and half y. So let us write the matrix corresponding to f. So it is just 2 and half with zeros here, that is the matrix corresponding to x1. The matrix corresponding to f2 is just, well, at 0 1 and x just means 1 0. So you should just check that what I am doing is right here, and this is just 2x plus 3y, so 2 3, 3x plus 4y, so 3 4. So this was our recipe for constructing the matrices from the formulas for the functions. And now let us do the following, let us compute the determinants of these matrices. Okay. So if you compute the determinant, it's just sort of the AD minus BC formula. Here it's a 1, this is a minus 1, 4 2s are 8 minus 9 minus 1. Okay. So observe that the first transformation has determinant 1, the remaining two have determinant minus 1, but in any case the absolute value, the modulus of the determinant is 1 in all three cases. Okay. So what does that imply? It says that, well, if you take f1 or f2 or f3, they all scale the area by a factor of 1. Okay. So the area dilation factor is 1 for all three of our functions, for f1, f2 and f3. Okay. So all three have the same area dilation factor, means that if you start with, since our initial configuration was a square of side 1, so what does this imply? I had a square of a unit square of area 1 to start with. No matter how it evolves, so no matter, so this was our initial configuration, and now how does the system evolve with time? You apply either f1 or f2 or f3 in order to get the next step, right. So in the next step is something, the result of applying f1, 2 or 3 to this guy. And now what do we do in the next step? You again apply f1 or f2 or f3, and what does that make it? Well, it might make it something else maybe, and so on. Okay. So this is how the configurations evolve with time, but what we know is that at each step the area dilation factor is 1. What does that mean? The area of this figure, whatever it may be, will always remain the same, because the dilation is just by a factor of 1. So these figures, whatever they are, all have the same area. Okay. So observe that gamma of C, we just said it's the area of the parallelogram. So gamma of C, which is the area in this case, remains unchanged, means constant as the system evolves. Gamma is the area. Okay. So let us use this to answer the question again. So here is the conserved quantity for this evolution rule. Okay. So as the system evolves, gamma remains, the area remains a constant. So the question we asked, is it possible at some point of time for these 4 points to form the vertices of a rectangle of area 6, is of course not possible, right. So because the area would be a 6 here, whereas the initial configuration that we started out with only had area 1. Okay. So you can never get these 4 points to make a figure whose area is 6, they will always only make a parallelogram of area 1. Okay. So these are two examples of conserved quantities, and where the fact that there is a conserved quantity allows you to make at least answer some questions rather quickly. The impossibility of attaining certain configurations can be quickly answered from this. Okay, so next time we look at a few more examples of conservation principles.